Going to discuss about power measurement in three-phase system. Now, power in three-phase system can be measured by 1 wattmeter method, 2 wattmeter method, and 3 wattmeter method. If we are measuring power using 1 wattmeter method, the system is to be balanced. However, the power measured in three-phase system using 2 wattmeter method and 3 wattmeter method is possible in unbalanced system as well. Now, considering a star connection. In case of star connection, we are having two wattmeters, and having two wattmeters, the power measure in two using two wattmeter. One wattmeter is connected in, let it is in R phase, another wattmeter is connected in Y phase, whereas third phase is made common for both the wattmeters. In this case, the current coil is connected in series with the R phase, whereas the current coil for second wattmeter is connected in Y phase, where the voltage coil of wattmeter W1 is connected between R and B phase, whereas the voltage coil of wattmeter second wattmeter is connected between Y and B phase, and hence the power measured by these two wattmeters depends upon the current of individual phases and the voltage of common phase, third common phase. Now similarly, in case of delta connection, the wattmeter is connected in the same way, because we are not measuring the individual power, we are measuring the power of three phases using two wattmeter method, and therefore the connection scheme for delta as well as star will be same. Now, if we are considering 3 wattmeters, in case of 3 wattmeter, we are connecting 3 wattmeter in each phase, 1 wattmeter in each phase. If it is W1 connected in R phase, W2 is connected in Y phase, and W3 is connected in B phase with respect to neutral. However, if the 3 wattmeters are connected in delta connections, then individual phase is considered rather than considering these lines, as the case of star connection, because in case of star connection the current flowing in this phase is same whatever current is flowing in this line. However, in case of delta connection, the current flowing in this line is not same as that of the current in individual phases. Therefore, this wattmeter is always connected in series with this particular phase winding. Now, the reading of this wattmeter is W1, W2 and W3. Therefore, the total power will be equal to sum of the reading of 3 wattmeters. However, if these 3 wattmeters having a multiplying factor and different multiplying factor for different wattmeter, then accordingly multiplying factor will be considered for individual wattmeters. Now, the most common method for power measurement in three-phase system is 2 wattmeter method. And in this class, we are going to discuss about 2 wattmeter method. Now, in this 2 wattmeter method, though there are 2 wattmeters, but we have to measure the power of 3 phases. In that case, we need to identify and how this 2 wattmeter can measure the power of 3 phases. Let me consider the phasor diagram of this star connected load. Here we consider the star connection. This is the phase voltage of R, this is the phase voltage of Y, this is the phase voltage of B. The current in phase R is lagging by an angle of theta, let it is theta. In case of Y phase, again it will be theta. In case of B phase, this will also be theta. Let me consider the system is balanced. Now, if this wattmeter, the voltage across this wattmeter, current coil, the current in this wattmeter is same as that of the current in this phase, whereas the voltage across this wattmeter is the voltage of R and B phase. Now, this is the B phase voltage, this is R phase voltage, this is Y phase voltage. In order to find out the voltage across this coil as a phasor sum of R and Y, R and B phase, then B phase voltage is reversed. Similarly, for this the second wattmeter connected in Y phase, the voltage across this coil is the phasor sum of Vy and Vb. And hence, this when we reverse this vector Vb, then it will be minus of Vb. P here denotes the phase value, phase quantity. Now, in this case, if this voltage is reversed and the Vr and Vb is the potential across W1, Vy minus Vb is the potential across W2. Similarly, from here, if it is minus Vb, the Vr and Vb is the potential across wattmeter W1, and Vr minus VB is the potential YB is the potential across W2. The current in this circuit is IL, and the current in this circuit is also IL. Since this is a balanced system, we consider IL ILR is equal to ILY is equal to ILB, and let it is simply written as IL. And the potential of these two coils have already considered using this phasor diagram. Then we can say the wattmeter, the power measured by this wattmeter depends upon the current in this phase, whereas the potential of these two phases, the potential of these two phases is measured as VRB, and for the another wattmeter it is VYB. The angle between this current and this voltage, in case of first wattmeter, the angle between the current flowing in this current coil, the voltage in the voltage coil, and the voltage coil. Now if the current is R phase is IPR, this is the angle between these two, because the total angle is 30 degree. This total angle is 30 degree, this angle is 60 degree. Then this angle is 30 degree, and if we can subtract 30, if we can have 30 minus theta, then this angle we can find out, this angle is nothing but 30 minus theta, this angle. And hence we can say for this wattmeter the reading is not only the because of the current and voltage of R phase. This is this depends upon cos of 30 minus theta, and hence if we want to measure the power, then W1 will be equals to VL IL cos of 30 minus theta, the line current of this, and this is nothing but the line voltage between R and B phase. Similarly for the second wattmeter, in second wattmeter the current in the coil is IL, that is IL is the current. The potential across this coil is V by B, and this V by B is the potential of this angle is, this total angle is 60 degree, this total angle is 60 degree, this angle is 30 degree, this angle is theta, and hence this current was flowing in the current coil of the wattmeter. This is the voltage across the potential coil of the wattmeter. This angle is, total angle is now 30 plus theta, 30 plus theta, and hence the reading of second wattmeter W2 will be VL IL cos of 30 plus theta. By the definition we know what is the reading of wattmeter, VI cos theta, because here the current between the angle between current and voltage is 30 plus theta and 30 minus theta, then accordingly W1 and W2 is defined. Now, by the definition, P, we know P is the phasor, is the algebraic, is the sum of all the instantaneous powers in a circuit. And if we are considering VR, IR, VY, IY, VB, and IB, then in star connection, by the definition we know IR plus IY plus IB is equal to 0. The sum of current at a junction is equal to 0, and IB is equal to minus of IR minus IY, and hence putting this value IB in this equation and rearrange this equation, then we can easily find out the power is, because of the two wattmeter, is given by IR into me phase difference of VR and VB. Similarly IY into me phase difference of VY and VB. This is the phase difference of VY and VB. This is the phase difference of VR and VB, and the current in this is IR, and the current here in the second wattmeter is IY. So now similarly here it is IR, this is IY, this is a phase difference of R and B, this is the phase difference of Y and B, and hence the reading of one wattmeter is W1, the reading of another wattmeter is W2. If instantaneous value is the sum of instantaneous power, then the average value of wattmeter reading will be the sum of average reading of wattmeter will be the will be the total average power. Now, proof of power measurement by using two wattmeter method. As we have already discussed that this wattmeter reading is given by the equation W1 is equal to VR BIR cos of 30, and here VR is nothing but VL, IR is nothing but IL. In case of star connection, we can say VL IL cos of 30 minus theta, whereas in case of W2 is equal to VL IL cos of 30 plus theta. Now, from these two wattmeter reading, if we are adding W1 plus W2, then it will give, after simplification of trigonometric function cos A minus B cos A plus B, then it will be root 3 VL IL cos theta. If we are subtracting W1 and W2, the resultant value will be VL IL sin of theta. From these two equations, if we are considering this is equation 1, this is equation 2, dividing equation 1 and 2, then it will be W1 plus upon W1 plus W2 upon W1 minus W2 is equal to this function root 3 VLIL cos theta divided by VLIL sin theta. So on simplification of this function, then we can easily find out the value of theta in terms of reading of wattmeter. Now, two wattmeter method in delta connection. The way we have discussed the power measured by different two wattmeter W1 and W2 is the same. In this case, we can find out the relationship between currents. Earlier, it was the relationship we obtained the relationship for voltage. Now, if the voltage apply across this phase is nothing but the voltage across this coil, potential coil. For this phase, this is this potential coil, whereas across this phase, if this is the potential across this phase, we consider the voltage drop in this within this wattmeter is negligible, and hence the line voltage of this phase is equal to this voltage across this coil. The phase voltage of this phase is equal to the potential drop across this coil. Now the current flowing in this current coil and the current flowing in this current coil is not equal to the phase current. This current coil is the phasor sum of these two currents. Similarly, this current coil is the phasor sum of these two currents, and hence in case of delta connected system, we need to find out the relationship between currents. Now by definition, we know this is the phasor of IR, this is the phasor of IY, this is the phasor of IB. Now this the current ILR is the phasor sum of IR and IB, and hence if we can reverse the phasor. Now similarly we can say the ILY is the phasor sum of IR and IY, and hence in both the cases IR is common. We have to take a reverse of this vector minus of IR. P again here represents the phase values. Now the phasor sum of these two currents IPR and IPB is nothing but IBR, the line current of two phases. Similarly, the phase sum of IY and IR is nothing but IYR, and that is nothing but the IL. This is also a IL. For a balanced system, all these values are same, whereas the voltages are same. This between these two lines is the voltage across this phase only, and hence we can say for W1 the reading is now the for W1 the current and voltages are the this is the current in first wattmeter, and this is the voltage in first wattmeter. This total angle is 30, and hence this angle will be between current and voltage will be 30 minus theta, whereas in this case this is the uh, voltage in y phase, this is the current in wattmeter, and this total angle, this angle is theta, this angle is 30 degree, and hence this total angle is 30 plus theta. And we can say the for wattmeter 1 the reading is VL, the line voltage is same as this phase voltage, whereas the current in this IL, the angle between IL and VL which is responsible for the reading of W1 is cos of 30 minus theta, whereas for W2 the reading is VL IL cos of 30 plus theta. And hence we can say the reading of wattmeter and wattmeter 2 in case of delta connection as well is given by this is defined by the same in the same way as VL IL cos of 30 plus theta and VL IL cos of 30 minus theta. And this is again proved over here. In case of delta connection, we know sum of voltage is equal to 0. Rearrange this voltage for VR and putting the value in instantaneous product of powers, sum of powers in individual phases. for the power for instantaneous power of phase R, instantaneous power of phase Y, instantaneous power of phase B. Putting this value in this equation and rearranging, then we can say there are two components which are current and voltage responsible for the reading of wattmeter are VB and I phasor sum of IB and IR, VY and the phasor sum of IY and IR. If instantaneous sum of instantaneous reading of wattmeter is the total power, then we can say the sum of average reading of wattmeter will be the total power, and hence P is equal to W1 plus W2. Now, in the way we have defined calculated the power factor angle of a load, here we can also calculate if it is W1, W1 will be equals to VL, IL cos of 30 minus theta. Similarly, W2 will be equals to VL, IL cos of 30 plus theta. Here, though we consider here the system is balanced, this is IL, this is nothing but IL, this is nothing but VL. In case of delta connection, phase voltage and line voltage are equal, and this is IL, this is VL, this is IL. Again, considering equation first, equation second, W1 plus W2 and W1 minus W2, we can easily calculate theta power factor angle of the load using two wattmeter readings. Now, in these two wattmeter readings, the reading of this two wattmeter can be influenced with the variation of this angle theta. If theta is equal to 0, then W1 will be equals to W2. If theta is equal to 30 degree, then W1 and W2 will be, in case theta is equal to 0, then cos of if is 30 degree, then it will be the reading of one wattmeter W1 will be equals to root 3 times of root 3 by 2 VL IL. If the reading of wattmeter 2 will be equals to that will be cos of 60 degree. Cos of 60 degree is 1 by 2 VL IL. Now, in case theta is equal to 30 degree, this value will be 0. Cos of 0 is, now in case of cos of 0 is 1, and hence the reading of this wattmeter is VL IL, and there another wattmeter VL by and half of the another wattmeter. Now similarly, if we consider theta is equal to 60 degree, then this will be 30 degree. Cos of 30 degree, reading of 1 wattmeter is W1 will be equals to root 3 by 2 VL IL, whereas the W2 will be equals to cos of 90 degree is equal to 0. Another wattmeter reading will be 0, and hence wattmeter reading can be influenced with the power factor of the load.